Today we shall discuss the hyperfine interaction and structure in the hydrogen atom. As the name implies, it is even finer than the fine structure, meaning that the energies involved are much less. And what's the physical reason of the hyperfine interaction? It is because proton, which sits at the center, has a magnetic moment. So let me write the electron magnetic moment and the proton magnetic moment. This is minus and the angular momentum, intrinsic angular momentum, this is, we are using S as a dimensionless, but the angular momentum has the dimension. So these things cancel. This is minus gs mu b s. This is the dimensionless spin angular momentum. And this one is the Bohr magneton. It's about roughly 6 times 10 to the minus 5 electron volts over Tesla. And we have the proton magnetic moment. It is plus Gp, then nuclear magneton. This is the Bohr magneton. This is the nuclear magneton divided by h bar times the spin angular momentum of the proton, and we take h bar out. So this is now dimensionless. It is Gp mu n sp. Here, by the way, Gs is 2 to a very good approximation, and here we have a plus. This is minus because electron has a minus charge, proton has a plus charge, and Gp has this value, and mu n is like that, but uses the proton mass. So it is E h bar over 2 mp. I can divide and multiply by me. So it is like mu b over, this is the ratio of the proton mass to the electron mass, something like 2000. So the nuclear magneton is about 2000 times smaller than the Bohr magneton. That's why we have the hyperfine structure, namely very fine structure. All right. So the physical simple picture is this. Here is our coordinate system, and proton is, which is about 2000 more massive than the electron, sits here. It's this is its magnetic moment, and the electron is somewhere here. And what is the interaction that goes into the hyperfine interaction? The magnetic dipole of the proton creates a magnetic field, B field. And electron, which is somewhere here, has a magnetic moment. It feels the magnetic field created by the proton, and it interacts with it. And the proton is at the center, at the origin, and it's here. This is the magnetic field it creates. Here it is. I wrote our physical because in our wave functions we are using dimensionless variables. Here it has the dimension, it has the length. So this is the form. This is the contact term. Namely, this is 0 when you look at it outside of origin, and at the origin it is a Dirac delta function. And this is the part that is effective when r is not equal to 0, away from the origin. So this is the magnetic field created by the magnetic dipole of the proton, and it interacts with the magnetic dipole moment of the electron. That's one effect. The second effect is that electron is orbiting about the proton. Therefore, it is a current, and it is creating a magnetic field. Proton is sitting at the origin, so we have to evaluate the magnetic field due to the electron orbital motion at the position of the proton, which is the origin. And this is that term. Our physical, this distance is where the this is the proton, and this is the electron, and this is our distance, our physical. And the proton magnetic moment interacts with this magnetic field. Put together again. Electron magnetic dipole moment interacts with the magnetic field created by the proton magnetic dipole. It has two terms. One is the contact term, effective at r equals 0. The other term is effective at r not equal to 0, away from the origin. And plus the proton magnetic moment interacts with the magnetic field created due to the orbital motion of the electron. So first we shall compute the hyperfine energies, and we will simply take this, use this interaction energy operator. In the second part of this discussion, I will derive this from classical electrodynamics. So right now we shall just use this one. Okay, so this is the electron magnetic moment. This is 2 Bohr magneton and dimensionless electron spin. And this is the proton dipole moment. There is this number, 558. And then nucleon magneton, which is about 2,000 times smaller than the Bohr magneton, and the dimensionless spin of the proton. So we shall calculate the energy. How does this influence the spectra? What is the energy difference? What are the level shifts? I am erasing this part. Let me just simply write here mu E is equal to minus GS mu B S electron. Let's put an index electron. All right. Mu P is equal to plus GP mu N SP. I am erasing this part. Now we shall again compute the contribution to energy in the first order perturbation theory. So we need the diagonal elements of H between hydrogen states. So a typical state, the orbital part is NL ML, which is R. This is now dimensionless, R N L R, and y, l, m, l, depending on the angle. Now, for L not equal to 0, contact term does not contribute because R goes as R to the L and it is vanishing at the origin. So no contact, no contribution from the contact term. No contribution from the contact term. So then these terms will contribute. If L equals 0, s-orbitals, then s-orbitals have, remember, they go as r to the L, there's e to the minus r, and a polynomial, like associated Laguerre polynomial. So this is just a polynomial. This one goes to 0 for non-zero L and no contribution from the contact term. For L equals 0, this is not there. R to the 0 is 1. And this is not 0. This is 1. Therefore, contact term contributes. Contact term contributes. But what about the other terms? Do the other terms contribute? For example, this and that. Let us show now in a simple way that they do not contribute for the S waves. These magnetic dipole moments are proportional to spin angular momentum. So we have three and we are integrating this we are taking the angular average because L equals 0, y00 is simply y00 is simply 1 over root 4 pi, has no angles. So we have to look at the angular integration here. We can write this integral as I. We are summing over I and j. This integral is trivial. This part is simply 4 pi. And we discussed this integral before when we discussed the Darwin term for the fine structure. And it's easy to find again. There is no direction defined, so I has to be equal to j. For example, R1 square is equal to R2 square, R3 square. All of them are 1/3, 4 pi delta ij. So the result is SEI SPJ. This is 3 times 4 pi over 3 minus 4 pi delta ij, and this is 0. 4 pi minus 4 pi is equal to 0. So the angular average of this part is 0. Only for the magnetic field of the proton, only contact term contributes to the S waves. How about this one? So I am erasing this part. Let us now show that this doesn't contribute either. So we have here SP dot L term, orbital angular momentum of the electron and the spin angular momentum of the proton. This, for example, what does it do to S waves? This operator we can write SPZ LZ plus 1/2 L plus SP. Let me write like this. SP minus L plus they commute anyway, so it doesn't matter. SP minus SP plus L minus, and this will act on N0, 0. So angular momentum operators LZ, L plus is, for example, Lx plus I Ly. This is Lx minus I Ly. So they all give 0. For example, the Z component of the angular momentum for L equals 0 is 0. These are the raising and lowering operators for the magnetic quantum number, but it is 0, so you cannot raise it and lower it. So this is 0. That means if we consider S waves, namely if we consider states N0, 0, all we have to consider is the contact term. So that's what we will do. Of course, for L not equal to 0, you have to do a lot more computation with all these operators. But we will only do the S waves, by the way, which are very important actually in spectra, as we shall see. So I will erase now this part. And so for L equals 0, for s orbitals, only the contact term interaction energy is only the contact term. Okay, so it is simply minus mu e to mu 0 over 3 mu p. Mu is dotting into mu p times delta R physical. So we shall only deal with this term. In the first part, I will compute the contribution of this thing to energy, and we shall discuss the results. In the second part of this discussion, I will derive this relation using classical electrodynamics. And in the third part, there is something very interesting about this coefficient, that it is 2/3. Okay, and the sign of it. It turns out that it is important, and it's telling us a lot about the intrinsic magnetic dipole moment of the proton. So that will be the third part. So I'm erasing all this. We don't need these anymore for the first part. I'm erasing it. Let me write here in detail. I will erase that part because we will need it. Equals. Remember, we are doing L equals 0 s orbital case. That's why we are keeping that. Okay. So I have mu E is minus GS mu B SE, and this one is plus GP mu B over times delta times S proton. So minus makes plus. It is plus 2 mu 0 over 3 GS GP over 36. Then I have mu B square then I have SE dot SP, then the contact term since we are using the electron spin and the proton spin, we must include them in our description of the state of the hydrogen. So the state, for example, psi will be n00 times the spin states. This is for the electron, 1/2 ms, and let me say me. This can only be plus f or minus f, and the proton spinner mp, that's also 1/2 and minus half. But these are not the wave functions to be used, just like in the fine structure study. Remember, there we had the term s dot l. So, namely, the z components of these operators are not good quantum numbers. So we do exactly the same thing here. The z components here, me, mp, are not good quantum numbers. Interaction changes them. So what is diagonal is the total spin, and we construct states Fm from 1/2 for the electron, 1/2 for the proton, like this, Me, Mp. Both of them go plus minus a half, plus minus a half, times the Clebsch-Gordan coefficient, 1/2 Me, 1/2 Mp, Fm, okay, electron 1/2 Me, okay, proton 1/2 Mp. So we should use these functions because F is a good quantum number, M is a good quantum number, but not Me or Mp. So our the states that we should use are not these, let me call them phi, but we should use these psi states, which are, let me write like this, n00 Fm, and Fm is this one. So we have to compute in the first order perturbation, delta E1 hyperfine structure is n00 Fm HF. We are simply using the contact term, n00 Fm. Now, since this operator is not acting on the spatial variables, only on the spin, we have this matrix element, Fm Se dot Sp Fm. So we have to compute that. So F is the total spin angular momentum. F square is SE square plus SP square plus 2 SE dot SP and SE dot SP therefore is equal to 1/2 F square. But these are simply spin 1/2 particles. So S square is S times S plus 1, that's the eigenvalue. So it is, and S is 1/2, so it is 1/2 times 3/2, which is 3/4, minus 3/4, minus 3/4. So it is 1/2 F square minus 3/2. Now, what are the possible values of F? It can go either SE plus SP to SE minus SP. So 1/2 plus, so possible values are 1 and 0. F equals 1, we call triplet. F equals 0, that's the singlet. So if F equals 1, and this has the F plus 1 minus 3/2. So if F equals 1, this matrix element is equal to 1/2 2, 1 times 2 minus 3/2, 2/2. So it is 4 minus 3 over, which is 1/4. So this is for the triplet. For the singlet, this is 0, so that's 0, minus 3/4 for the singlet. Minus 3/4 for the singlet. It's triplet, this is the singlet. Okay. So I can write this thing as equal to, that this matrix is equal to, let me write simply like that. This is 1/4 minus 3/4. That's it. This is a triplet. This is the singlet. I can erase now the spin calculation. All right. What can I erase here? I can erase this one. I can erase this one. So let me erase some things. I am trying to compute that one. Okay. Now let me write delta E1 HF. Remember, we are doing for the L equals 0, and from that complicated interaction term, we only took the contact term. First, we have these constants, 2 mu 0/3, GS, GP over 36, mu B square. Then I have this Fm, SE, SP, Fm, times N00, delta R physical, N00. We have not computed this one yet. And this one we found 1/4 minus 3/4. This is for the triplet, this is for the singlet. And all we need to compute this one now. I'm erasing this. We were using dimensionless distances in our wave functions, therefore let's convert that. R physical is R0 times R, this is the Bohr radius, Therefore, delta R physical is equal to 1 over R0 cubed delta R. Now, therefore, this thing and 0, 0 delta R physical and 0, 0, this just gives me R and 0, 0 square, and y, because of 0, 0, y 0, 0 absolute square. We took these functions real. Y0, 0 is also real. All right. R and 0 is square, is n and 0 square. And we are, and this is L equals 0. And we are evaluating it at R equals 0. N and 0 square. Then e to the minus 2r over n, but r is 0, so that's 1. But this is not 0. And this is, remember, we have L12 plus 1, n minus L minus 1, 2r over n. So here what we need, L equals 0, L1, L equals 0, n minus 1, and r is equal to 0, 0. Okay? We need the square of that. And one has to be careful because there are many, there are different normalizations of the Laguerre polynomials. The one we were using all throughout in these hydrogen atom discussions were such that L alpha n 0 was this of n factorial. So here we have equals alpha is 1, n is, so it is 1 plus n minus 1 factorial divided by 1 factorial n minus 1 factorial. Namely n factorial divided by n minus 1 factorial. So it is simply n. So this is equal to 1 over, we have n over 2, 2l plus 3, l equals 0, that's 3, 2n, then n plus l factorial, l equals 0, so I have n factorial, then n minus l minus 1 factorial, l equals 0, it is n minus 1 factorial, times the square of it, n square. So this is 8, 8 is on top, divided by 2, that's 4, n to the 5, n square, so it is 4 over n cubed. All right, this is that. And we also have this, so that's equal to 4 over n cubed, and y0, 0 is 1 over root 4 pi, it's constant, so it is 1 over 4 pi, this cancelled, it is 1 over pi n cubed. So we computed this one, this is equals 1 over pi n cubed. All right, now let me erase everything and collect things together. So I'm erasing the board. All right, so let me write again. I'm starting from here. Delta E1 HF is equal to, Now I will also multiply by epsilon 0, divide by epsilon 0, and notice that epsilon 0 mu 0 is equal to 1 over c squared. So I have 2 over 3, 1 over epsilon 0 c squared. There are many terms. The thing is to group them together nicely. Epsilon 0 square. I handle this. GS GP over 36. I am here. Then I have mu b square. That's E square h bar square 4 m electron square. Remember, mu b is E h bar over 2me. So this is the square. I am here. Then let me write 1 over pi n cubed. Our physical is, we wrote this, we forgot r0 cubed. So this is 1 over r0 cubed delta r. So I have to divide by r0 cubed, r0 cubed, r0 cubed. Okay. So r0 cubed. R0 is the Bohr radius. Okay, then I have this spin matrix element. It is 1 over 4 minus 3 over 4. This is triplet. This is singlet. Now, what do we recognize something? Indeed, yes. Let's take this 4, this pi, and this epsilon 0. Let me write it like this: 2 over 3 GS GP over 36. Then I have E square over 4 pi epsilon 0, 1 over r0. Then I have h bar me c square. Pi is gone. 1 over n cubed times this thing. 1 over 4 minus 3 over 4. This is for triplet, this is for singlet. Do we recognize something? Yes. This is the minus the potential energy of the electron in the hydrogen atom. And we know, even from the first lecture of the series, that this is 2 epsilon. Epsilon is the binding energy. 2 epsilon 0. This is the 13.6 electron volts. 13.6 electron volts. All right. Do we recognize this? Remember, we discussed this term in the Darwin term when we were discussing the fine structure. H over MEC is the Compton wavelength. If you divide by 2 pi, and lambda over r0 is equal to alpha. Remember, r0 times alpha is lambda. Therefore, we have an alpha square here. Let me again collect. Let me collect here. That's equal to I will take the 2 to here, so it is 4 over 3 GS GP over 1836. Then I have E0 and E0 over n square. Let me write like this. Then I have alpha square coming from here, alpha square over n times 1 over 4 minus 3 over 4 for triplet and for singlet. If you notice, this is simply the absolute value of the unperturbed nth energy level, and this whole thing is the amplitude AN we have been using for the fine structure when we studied fine structure. So I can erase these now. So the let me write like this: delta E1 HF, we are doing for L equals 0 for general n, that's equal to, this is the triplet energy minus the singlet energy, that's equal to, GS is 2, so it is I have AN times 8 over 3 times GP 36 and 1 over 4 minus 3 over 4, 1 over 4 minus 3 over 4 is 4 over 4, that's equal to 1 times 1. All right, that's it. This is the where AN is E0n times alpha square over n. E0n is E0 divided by n square. This is the 13.6 n square. Okay, so that's it finally. Namely, our levels split, triplet and singlet. This is the energy the difference. Let's compute numerically for n equals 1. So the delta E1 HF for n equals 1, and for when n equals 1, L is necessarily 0. That's equal to 13.6 electron volts. Then I have alpha square, 1 over 137, 1 over 137. Then I have 8 over 3, 8 over 3. And this is 5.58 divided by equals, let me erase this part. So delta E1 HF n equals 1, L equals 0, and I'm looking triplet minus the singlet energy difference. Triplet is above. This is in electron volts. This is 0.1. This is gone. This is 1 over 137 times 8 over 3. If you notice, this is 55. 3 times 18 is 54. So roughly speaking, this is 3 times 10 to the minus 3 this knocks it off. So it is 8 over 137 times 10 to the minus 4, or 800 divided by 137 times 10 to the minus 6. So this is roughly 140. So what is it? 6 times 84. So if you write 6, this is 840. So it's a bit less than 6. So something like 10 times 10 to electron volts. 10 to the 6 electron volts. So this is the energy difference between n equals 1. And if you look at the triplet and the singlet, this is the energy difference delta, which is 6 times 10 to the minus 6 electron volts. All right. Now, I want to say, where is our state, by the way? I'm erasing everything here. Okay. This is our ground state, Bohr ground state. This is at minus 13.6 electron volts. Minus 13.6 electron volts. Now, fine structure energy is for this level E0, n square is 1, then I have alpha square, n is 1, times 3 over 4n minus 1 over j plus a half. That's the fine structure energy shift. N is 1, and because L equals 0, j is 1/2. So this is 3 over 4 minus 4 over 4. That's equal to minus 1 over 4. So this is numerically 13.6 electron volts divided by 137, another 137. And then I have a minus 1 over 4. Let us estimate this roughly. This is 0.1. And this is like 1 over 140 times 4. This is 0. This is like 56, 560. So this is roughly 0.1 times 2 times 10 to the minus 3 electron volt, and this is roughly 2 times 10 to the minus 4 electron volts. So this state of hydrogen through fine structure comes down to here. This difference is 2 times 10 to the minus 4 electron volts. Then what happens? This is 1s 1/2. There is something we mentioned but we did not calculate, and that's the lamp shift. The true calculation requires relativistic quantum field theory. What essentially says is that we have been treating the electromagnetic field classically, but we should do that quantum mechanically, and this field has fluctuations which affect the energy of the electron. And for L equals 0, it has a simple expression, and it is like this: an, the same an times alpha over 2, and what people call as kn and L equals 0. This is a number 12.7. For different L, it has different values, and that's it. So, how big is that? For n equals 1, again, 13.6 electron volts times alpha square, 1 over 137, 1 over 137. Then I have another 137 times about 6. 12.2 divided by 2 is 6. So this is 0.1 electron volts times, this is like 140, 14 times 14 is 196, say 200, 0 times 6, so it is 1, this is 3, 1, 2, 3, 4, another 1, so it is roughly 3 times 10 to the minus 5 electron volts. So this is shifted up now by 3 times 10 to the minus 5 electron volts. The computation involves many Feynman diagrams. You may hear the names. Especially important diagrams are those. I don't need to show them here, but just mention the names. Vacuum polarization, that is described by a Feynman diagram. Electron mass, renormalization, and anomalous magnetic moment. These are the most important terms that contribute magnetic moment. Okay, so however, you must do the relativistic quantum field theory. But for L equals 0 terms, the result is simple, and if you evaluate for n equals 1, this is the term 3 times 10 to the minus 5. And we found, therefore, this is shifted, and now this is the triplet. I'm exaggerating, triplet, and this delta is like 6 times 10 to the minus 6 electron volts. Okay, so our S level went down due to the fine structure by roughly 2 times 10 to the minus 4 electron volts, pushed up by the lamp shift by 3 times 10 to the minus 5 electron volts. We give the result, but not the derivation. And the magnetic interaction, dipole-dipole contact term, gives different energies for the triplet and the singlet, and the difference is 6 times 10 to the minus 6 electron volts. Fine. Now, there are some interesting results. So I will erase this. So this difference, delta, of course, you can have a transition. This delta is 6 times 10 to the minus 6 electron volts. That is H times F, or H C over lambda, or I can write this thing as 2 pi H bar C over lambda, or 2 pi. H bar C is, roughly speaking, 2000 electron volts times angstrom divided by lambda. That's 6 electron volts. So this thing cancels. 2 pi is roughly 6. So lambda is 2000 angstroms divided by 10 to the minus 6, which makes 2 times 10 to the 9 angstroms. 10 to the 10 angstroms is a meter, so let me multiply by 10 divided by 10. So many angstroms is a meter, so it is 2 meters divided by 10. So it's roughly 20 centimeters. If you do it more correctly, lambda, now this is the famous result. This is the, if you do it more correctly using calculator, etc. This is 21 centimeters. So this is the 21 centimeter wavelength coming from the hyperfine transition of the hydrogen ground state. Namely, ground state splits into 2. Ground state is really the singlet state. This is the lowest state. But if you excite it to the triplet state, it comes down with a 21 centimeter, emitting a 21 centimeter wavelength. Let me just also compute its frequency. All right. F lambda is equal to C. C is 3 times 10 to the 8 meters times 10 to the 2 centimeters divided by, let me use 20. So 1.5 times 10 to the 9. So times 10 to the 6. So roughly speaking, 1500 megahertz. So when the hydrogen, if you excite it to the triplet state and it comes down to the singlet state, it emits a photon with a frequency of 1500 megahertz or 21 centimeter wavelength. It turns out this is extremely important in astrophysics. It is so important, I better say a few words about it. First, notice that 21 centimeters, well, it's about this big, all right? It is bigger than the dust size, so it can penetrate through the regions with dust, so we can still detect it. Namely, it comes to us, it doesn't just scatter off and disappear, it comes to us. So we can spot it from, there's hydrogen somewhere here, and if it's makes a transition, hyperfine transition, we can detect it on Earth. Now, there is something very interesting about this. Let me erase this, we have done. The interesting thing is that our universe is filled with a uniform radiation called cosmic microwave background radiation, CMBR. Cosmic microwave background radiation. These are the photons that were released in the year around 380,000. We are now in the year 14 billion from the starting of the universe. And it fills the whole universe uniformly. And today, remember, this is the radiation that was discovered by Bob Wilson and Arno Penzias, for which they got the Nobel Prize. Which was predicted by Gamow and his students. Now, the temperature of this cosmic microwave background radiation is about 3 degrees Kelvin today. Today we measure it at 3 degrees Kelvin. So, what is the energy of these photons, the average energy? kBt room, like in this room now, is roughly speaking 1/40 electron volts. So, what is kBt cMBR? So, kB T room times T cMBR divided by T room. This is 1/40 electron volts, and this is 3/300. 3/300. So it is 1. So it is 1/4000 electron volts. So it is what? 10/4 is 2.5. So 2.5 times 10 to the minus 4 electron volts. So these photons that fill the whole universe, this room, the garden, beyond our Milky Way, everywhere in the universe, these photons have on the average 2.5 times 10 to the minus 4 electron volts. Whereas our hyperfine levels have 6 times 10 to the minus 6 electron volts. Therefore, obviously 2.5 times 10 to the minus 4 electron volts is larger than 6 times 10 to the minus 6 electron volts. What does that mean? It means that if you have an atomic hydrogen, by the way, you can find atomic hydrogen in space. In the Earth environment, you find them as H2 molecule, and you have to separate it out, things like this. But you can find them as free hydrogen atoms in space. So wherever they are, they can easily be excited by the cosmic microwave background radiation, wherever they are. And then they will emit this 21 centimeter wavelength radiation, which is the telltale sign that it is the hydrogen atom over there. And here on Earth, here Earth, and we receive it, okay? This 21 centimeters. And then we say, aha, there is hydrogen over there. And by the way, I did not see the original papers, but I read about it, and it says that our Milky Way, which has spiral arms, these have been discovered due to this hyperfine transitions that we can discover. And we can discover the presence of hydrogen everywhere in the universe when we receive this 21 centimeter wavelength. One cannot help by thinking that many eons later, perhaps there is no more sapiens on Earth, perhaps there is no Earth anymore. When temperature of the universe drops, why is it dropping? Because the universe is expanding and the temperature of the cosmic microwave background radiation is dropping. So when this energy drops below 6 times 10 to the minus 6 electron volts, then you cannot excite the hydrogen atoms anymore. So if in some other galaxy, here's a star, there's another planet, and there are some beings who become smart and want to learn about the universe, they will not be able to observe this 21 centimeter radiation. They will not be able to tell that the hydrogen exists. So we are lucky that this is the situation, then we can see it. Another thing perhaps I should mention about the hyperfine structure is that this is just a remark, but I think we should talk a little about it. There is a much heavier atom, cesium 133 with 55 protons and electrons. Of course, it's a big atom. But the thing is that it has an inert core, xenon, and we have a 6s electron, which exhibits this clearly, this hyperfine transition. And there you don't have 1 and 0 because the nucleus of the cesium atom has 7.5 magnitude spin, not 1/2 but 7.5. So this is F equals 4 and F equals 3. So it makes this radiation, and this lambda is in the microwave. Perhaps this is one of the reasons that they chose this one, because microwave technology was highly developed during the Second World War time and was used in atomic physics. So this is about 3.26 centimeters. Okay. What is interesting about this transition is that we are using it as the definition of second. This is our time definition. Before then, here is Earth. Earth is going around the sun. Here is the sun. Okay. So in 1 year we are completing the turn. But if you define second with this motion of Earth about the sun, well, you wouldn't get to very high accuracies. For example, the accuracies needed by the global positioning systems. You have to be very, very highly accurate there. And this does it. And the error is about 1 second in 1.5 million years. And imagine that sapiens have been around for a few 100,000 years. So it's you don't mind this much error. All right. So finally, let me just state the order of magnitudes again. We have the, let me erase, which one? Let me erase this one. We computed in the previous discussions fine structure, and here we see that we have the Lamb delta E1 Lamb shift was something like of the order of alpha times delta E1 Fs. Okay, this is to the power alpha to the 4th, so this is alpha to the 5th, and delta E1 hyperfine is like basically there are some other factors, 2s and 3s, etc. It's not important, but the characteristic is MP over ME times delta E1 Fs. So it is 5.58 divided 3 times 10 to the minus 3. Okay. So these are the relative sizes of these energy shifts. Okay. If I want to wrap it up, we discussed for n and L equals 0 for s orbitals, the hyperfine structure. We calculated that exactly in the first order perturbation, exactly in that sense. And we have found this for the n equals 1, this 21 centimeter transition, which is exceedingly important to tell us about the hydrogen distribution in the universe. Next, in the second part, I will discuss the interaction operator, which at the beginning I simply wrote down, and we operated with the contact term. But I will use classical electrodynamics to obtain that form. All right, in this part, we will compute the interaction energy. That's all right. The first part is what is at the origin. We have the proton, which is a magnetic dipole. The question is, what is its magnetic field everywhere? All right. Well, we have to start someplace. We cannot begin from Adam and Eve. So the point I want to take is this. Maxwell's equation says that divergence of B is equal to 0, and that B therefore can be written as curl of A. And for a magnetic dipole, which sits at the origin, A is mu0 over 4 pi m cross r over r cubed. I want to shorten the notation. I will just use mu p is equal to m, because there is a subindex, and I want to use it without a subindex. And m is, so here m is not mass, it is simply the magnetic moment. So we will take its curl to get the magnetic field. But remember, we had a contact term, so we can think of it like this. Let us write the magnetic field and integrate it over volume V. Here's our magnetic moment m. This is the radius r, and I'm integrating it in a volume smaller than r. Of course, we'll let r finally to be infinitesimally small, going to 0. So the integral, let me call this f. The integral is a vector because B is a vector. This is therefore is equal to B is a dV. It would be easy if we do this. Take a constant vector, arbitrary vector, and let's dot it into F. So it will be A dV, and I can write this thing as AI. This is epsilon ijk. I'm using the Levi-Civita tensor notation for the cross product. Delta J AK. Since AI is constant, by the way, delta J is d by dxj. This goes 1, 2, 3, x, y, z. But A is a constant vector, so AI delta J is equal to delta J AI. So I can bring it in and out. So let me write it like this, minus epsilon J I K delta J AI AK. What happened? We wrote A dot F as minus integral dV divergence of A cross A. To which we can apply the Gauss's theorem, which means minus r square d omega r dot a cross a. This is equal to minus r square d omega a dot a cross r which I can take it out, a dot r square d omega r cross a. But this is now over the surface, not in the volume, but this is a surface integral. So I am erasing some things here. This is now taken over the surface. A dot f is equal to dot r squared d omega r cross. Now where is our a? It's here. Mu 0 over 4 pi m cross. This I can also write as mu 0 over 4 pi m cross r unit vector divided by r squared, where r unit is r over r. Except the magnitude of r is now capital R because we are at the surface. So it is m cross r divided by r squared. So this r squared knocks that off. So it is a mu 0 over 4 pi a dot. Now I will switch these and then flip r cross m cross r. Omega. This is m r dot r minus r m dot r. The omega. This is just 1. And I can write like this. The first term is mu 0 over 4 pi a dot m minus mu 0 over 4 pi a I m j times the omega here r I r j. But we have done this integral several times. This is simply 4 pi over 3 delta I j. So this is equal to mu 0 over 4 pi a dot m here this is 1. The integral gives 4 pi. Where's 4 pi? Let me write here 4 pi. This is 4 pi minus 4 pi over 3. So 4 pi is cancelled. 1 minus 1. So it is 2 mu 0 over 3 A dot M. We are finished. What have we done? All right, I can erase this computation. What have we done is that we have shown that F is A dot F is equal to A dot to mu 0 over 3 M. So since A is an arbitrary vector, constant vector, and this is true for all possible A's, the F, which is just this integral, is F equals B dV equals 2 mu 0 over 3 M. I am erasing the calculations here. But F, which is just that, is just this integral where we are integrating inside the sphere of radius r, but we can shrink this r to the point as small as you want. It doesn't depend on that. We simply have a finite result, even if you make the volume very, very small. Therefore, we can write B as 2 mu 0 over 3 M delta R. Here R is the physical R. Let me just physical plus B other. I will not in this part we don't, since we will not use the atomic wave functions which are computed with dimensionless variables. By R here I mean R physical. Plus B other. This part will be basically for R positive. This only operates at, so this is the contact term, contact. So B other will contribute nothing to this volume integral. So at R equals 0, this is effective. So we will find B other in a standard way by simply taking the curl of this thing. I am erasing. So B equals mu 0 over 4 pi curl of M cross R over R cubed. And now we are considering R not equal to 0 because R equals 0 contribution is basically this contact term. All right, so we have let's just take the ith component of it. So let me write mu 0 over 4 pi minus 1 bi to get rid of this thing when we calculate the rest. So the I component, this is a cross product of a cross product as a vector operation. So it is epsilon I j k delta j times the k component of this thing. M cross R over R cubed k component, which I can write as epsilon I j k delta j, then epsilon k a b m a r b divided by R cubed. I can take this one here, jumping 2 steps, which is a plus sign, and epsilon k I j epsilon k a b summed over k. I'm using the Einstein convention. There is a sum over the repeated indices. So here in this combination, K is summed over. And the result is, that's the property of the Levi-Civitas, delta IA delta JB minus delta IB delta JA. Okay. So it is equal to this thing with deltas. M is a constant, so M does not differentiate. MA, then delta J RB over R cubed. What is that? Let's look at here. Delta J RB over R cubed is equal to, first, you see delta J is d by dx or d by dy or d by dz. RB is either x, y, z. So if it's differentiating it, only contribution is when J is equal to B over R cubed minus RB. It will differentiate R minus 3, so plus minus 3 times RJ. This was 3 halves x squared plus y squared plus z squared raised to the power 3 halves. So this will be r to the 5, which I can write as delta JB minus 3 RA. This is the component of the unit vector now. RB, divide both sides, both parts by R cubed. You see, this thing is a symmetric tensor, symmetric Cartesian tensor. Let's call it TJB. And all right, now we need more space. So I have this result multiplied by MA and TJB equals, all right, let's follow. The first one, it says that I'm looking at the ith component. It says that A must be equal to, so I have MI, J must be equal to B, so it is simply trace of T, trace of this tensor, minus I is equal to B, it says A, and let's look at the second term. I did the first term. T has two terms, right, in it. But now I'm just looking at T. J and A must be the same. And so this is T, I, J, MJ. I can write it cleaner now. Mu 0 over 4 pi minus 1 Bi is equal to B is equal to M times trace T minus T let me write like this, MT, T is symmetric so it doesn't matter, MT I. This is MJ TJI. Okay, So we need to compute first trace T. I can erase many other things. I'm done here. All right, let's compute trace T. T is here. So trace T times r cubed. I'm just take the trace of it. Trace of the unit matrix is 3. This is minus 3. A is equal to B, and sum over, that's 1. 3 minus 3, that's equal to 0. So trace T is equal to 0. So what are we left with? Mu 0 over 4 pi minus 1 B is equal to, this gives me an m over r cubed minus 3 m dot r over r cubed. We are finished. B is equal to mu 0 over 4 pi m over r cubed minus 3 r dot m divided by, again, r cubed. So we will add this B to here. B is 2 mu 0 over 3 m delta r plus mu 0 over 4 pi we had a minus sign here, so it is minus m plus this. Okay, we have a minus sign here, therefore minus goes with that, and minus minus plus. Mu 0 over 4 pi 3 r dot m over r cubed minus m over r cubed. Finished. Now we can use m equals mu proton, okay, and mu proton for our case was g proton mu n over h bar s proton. Okay, becomes a quantum mechanical operator, magnetic dipole operator. So instead of m, we should put mu p. So this is the everywhere. This is the B field due to the proton magnetic dipole. So this part we have done. Okay, let it stay. Next we shall compute the magnetic field due to the orbital motion of the electron at the site of the proton. So I am erasing all these. All right. Next, we shall calculate the magnetic field due to the orbital motion of the electron. We will calculate this magnetic field at the position of the proton, which is the origin. That's why 0 is there. So let's take a simple model. Here's an electron going with velocity v, and the B field To compute the B field here, let's take a current element, let's say dl, and we draw from the source to the field point. The field point is where the proton is. So I will call it R. But R is not from the origin out, from the position of the electron into the center. Okay. B of 0 is mu 0 over 4 pi. Then dl cross R over R cubed. And we are times I, times the current. Now we will take it over this circle. Let's say circle of R, or let's say R. dl magnitude is so. dl magnitude is, this is d theta and R, so the line is rd theta, rd theta. And R is constant here, only the vector direction is changing. But let's look at this. dl cross R. R is into the center. dl is always tangent, and if the electron was here, its velocity would be parallel to dl. So dl cross R is out. So dl cross R magnitude is R squared d theta, and the direction is out of the blackboard. So this gives me, the integral is trivial because R is constant. This gives me 2 pi. So the result is mu 0 I over 4 pi R square divided by R cubed, they are constant, times the direction, times 2 pi, the integral of d theta, times the direction. Let me just show the direction like this, which is mu 0 I over 2R, and this is the direction. Now what is I? I is electric charge times the frequency, and we can write this thing as V over 2 pi R, which I can write as E V over 2 pi R. Let me multiply by mR divided by MER. Me is the electron mass. So it is equal to mu 0 over 2R. That's, now the current is E over 2 pi MER square, 2 pi MER square, coming from the second part. And I have this, let me write this as R MEV times that. This part I can write as, this is R times mv is just the magnitude of the angular momentum of the electron. So I can write this thing as R cross P electron. But angular momentum is R cross P. What is this minus R cross P? This minus R is from the choice we made at the beginning. Okay, it was into the blackboard. So this is simply the electron angular momentum, which I will write as h bar L operator. Never mind this minus operator. This is just designed to get this out of the blackboard direction with the definition of R to be consistent we have been using here, that it was into the blackboard. And one more, let me collect so far. That's mu 0 over 4 pi E over ME R cubed, R and R square, R cubed, H bar L operator. We are not finished yet. Let me write this as E is electron charge, which is minus E. So let me write it. Minus mu 0 over 4 pi E H bar over ME R cubed L operator. That's the E at 0. Now let's write this again, putting it all together. Putting it all together. H hyperfine interaction is minus mu E dot to mu 0 over 3 mu p. Now I write instead of m mu p delta r plus mu 0 over 4 pi 3 r dot mu p over r cubed minus mu p over r cubed. Now I am here, minus mu p minus mu p dot I'm copying from here, minus mu 0 over 4 pi E H bar over M E R cubed L operator, which is dotted into me. So this is the hyperfine interaction that we obtained using classical electromagnetism. And in the computation, quantum mechanical computation, we simply used only that one for the S waves. Now we have computed the energy shift due to this term for the S waves, and we have derived the interaction term. Now in the last part, we shall discuss something interesting about the contact term. It turns out that this contact term is telling us something. If we are careful and observant, we may notice something very interesting. That will be the subject of part 3 of this discussion. Now I am erasing stuff. Now, in the third part of this discussion, which is basically a continuation of the second part, where we discuss the forms of these fields, this is interesting. And this is telling us something. This is telling us something about the intrinsic property of the magnetic moment of the proton. And so let's look at this. I want to begin with considering the electric field due to a electric dipole at the origin. Consider a particle having an electric dipole, point dipole, and it is just like our proton was sitting at the origin. This P is not for, although this is a proton, this P is for electric dipole. And again, from elementary physics, we know the electric potential is 4 pi epsilon 0 P dot R over R cubed. And electric dipole is a you have minus QE minus Q to plus Q, and this is D. This distance is D. There's a direction, and this is equal to P. Q D is equal to P. All right. We just will do the same things we did for the magnetic field, for the electric field. So the first thing is, electric field is obtained by the gradient of phi. And let us integrate the electric field, just like we did with the magnetic field, in a sphere of radius r, and then we will let r shrink almost to 0. So we are looking for F, which is E dV, which is minus delta phi dV. Again, let me just take an arbitrary A constant, arbitrary vector, and I'm looking for A dot F, and it is minus A dot del phi, which I can write this thing as minus del dot A phi. Why? Because this is a two operation. One is a vector operation, the other one is a derivative operation. So when the derivative operates on A, namely the divergence of A is 0. So this is again A dot gradient of phi. But now I can use the Gauss theorem on it. So it is minus r square d omega r dot A phi. So, which I can write as A dot minus omega r square r times phi, and phi is here. So it is A dot minus the omega r square r P dot r over r square. R squares cancel. So A dots into R. So this is equal to minus AI Pj d omega Ri Rj. But we have encountered this integral so many times. We know the result. This is delta Ij times 4 pi over 3. With the result minus, there's a 4 pi epsilon 0 associated with it. 4 pi epsilon 0 phi is 4 pi epsilon 0. So 4 pi's go. It becomes A times minus P over epsilon 0. P over 3 epsilon 0. Since A was an arbitrary constant vector, therefore F, which is the volume integral of E over this small volume, F itself, which is E dV, that's equal to minus 3P over epsilon 0. Now we can let this R shrink. So we are integrating over an infinitesimal volume, almost of measure 0, and you are getting a finite result. Therefore, the E electric dipole has a contact term. This is minus 3P epsilon 0 times delta R. So if you integrate over dV, delta R dV gives me 1. We get back this result. So we have E 3P epsilon 0. We don't need to do further more, but just for the sake of completeness, let us find E also for non-zero R. So I don't need this F anymore. So we simply take this derivative for R not equal to 0. EI is minus delta I phi, which is minus delta I. Phi is 1 over 4 pi epsilon 0 PA RB over R cubed. So it is minus PA over 4 pi epsilon 0 delta I RB over R cubed. But this is nothing but the previous tensor we found, TIB. P dot R, PARA. TIA. Which is delta IA minus 3 RI RA over R cubed, which gives me 1 over 4 pi epsilon 0 3 R I R dot R unit vector dot P divided by R cubed minus P. We are finished. Let me write it here. Here I have a P at the origin. Its electric field ER is equal to minus 3P over epsilon 0 delta R plus 1 over 4 pi epsilon 0 3R R dot P. This is PI. I was calculating the ith component. 3R R dot P over R cubed minus P over R cubed. There's an R cubed here. And this is when you have an M. I'm erasing it. Now, these terms look similar, but these are different. Sign is different, and sort of magnitude is different. This is not 3, 1 over 3. I erased it, but 3 epsilon 0. Well, again, why should we think more about this? And it is because of this. Let me write the Maxwell's equations in the MKS system. Divergence of, now I'm writing Maxwell's equations. This is equal to rho electric over epsilon 0, and divergence of B is equal to 0. Faraday's law is E minus delta B delta T is equal to 0. This is C square electric current density divided by epsilon 0. All right. We have not observed magnetic charges, and that's why we have two homogeneous equations. With electric charge exists and it gives a density and a current density. So these are inhomogeneous equations. But suppose there were magnetic charges. What would that be? How would the equations change? Now note E and CB have the same dimension in the MKS system. So if you multiply it by C, this would go rho m has the same dimension as rho E. This is our definition. We are defining Jm. Suppose there were magnetic charges as Je. So this I would multiply by C, divergence of Cb. This would be rho m over epsilon 0. And this equation would go like this. Here I have dE dt, whereas here I have E over length. So to change 1 over length to 1 over time, you have to multiply by L over T, which is velocity, which is of course the speed of light. So we write minus del cross CE minus delta delta T CB is equal to Jm, the magnetic current density, divided by epsilon 0. Are we doing correct? Let's take the divergence of it. The curl of the divergence is 0 minus d by dt. Divergence of CB is equal to divergence of Jm over epsilon 0. This thing would be rho m over epsilon 0. Epsilon zeros would cancel. So this is nothing but d rho m dt plus divergence of Jm is equal to 0. So this is the continuity equation for the magnetic charge. Continuity. So our equation is correct. Namely, this is correct. I wrote it that way because that's the combination gets Jm over epsilon 0. Fine. So if there are magnetic monopoles, magnetic charges, this is the way we would, you would not throw away the Maxwell's theory. This is the way you would turn the homogeneous equations into inhomogeneous equations. The point is that these equations have a symmetry. If you let E, now I'm talking about the symmetry. If you let E go to CB, CB go to minus E, and rho E go to rho m, and rho m go to minus rho E, and Je go to Jm, and Jm go to minus Je. Okay? The Maxwell's equations go to the same Maxwell's equations again. Let's do one. You can check for yourself the others. Let's check this one. Del divergence CB going to minus E, minus E. Rho m is going to minus rho e, so it is minus rho e over epsilon 0. Minuses cancel. Divergence of E, we get this one. So if you do these changes, you get back the same equations. So the equations are symmetric in that. Now, what does it have to do with our problem? Our problem is that if you make such a change, then the electric dipole goes to the magnetic dipole, and we should get back the field. So let's do that on this electric field. I will let E go to CB, and P, remember, was Q times D. So let me just erase this part and do it on the electric field. The question is, can we get the magnetic part? So I'm just using this, nothing should change. I should get back this same thing. So I am making the changes on this field. So this becomes CB equals minus P. P is QE times D, so it is QM times D, which becomes, let's say, M over 3 epsilon 0 times delta R plus 1 over 4 pi epsilon 0 3R R dot M over R cubed minus M over R cubed. Wait, we are not finished yet. This M, of course, would be QM times D. Like P is QE times D. Notice that in electrodynamics, this, by the way, that M and this M are not the same. You will find out. This is mu P. Let me just go back from M to mu P's here. Okay, this M is QM times D, just the analog of the electric dipole moment. Okay, so I multiply by mu 0, mu 0, mu 0, mu 0, and epsilon mu 0 is 1 over c square. So I have a c square up and c square up. So one of the c's cancel. And we will write Cm is equal to mu P, the magnetic dipole. You see, we don't have the same units for electric dipole moment and magnetic dipole. Energy is either minus E dot P or minus E dot mu, but E is not of the same dimension with B. So multiply by C, divide by C. So P has the same dimension as mu over C, or mu is P times C. So these C's will become mu. So the B will be minus mu 0 mu over 3 plus mu 0 over 4 pi C times M I will call mu now 3 R dot mu over R cubed minus mu over R cubed. Let us now compare. Equations are invariant under this transformation. So with that, we are getting minus mu 0 over 3, where we got 2 mu 0 over 3. All right? Now, there is a discrepancy, of course. This must be telling us something, comparing with the experiment, it must be telling us something about the intrinsic magnetic dipole moment of the proton. So what is the difference? Let's write here. There are two differences. One is the sign. Second is the magnitude. Okay? That is, so if you multiply it by the same minus mu e dot b proton, okay? Here we have a factor of 2. Here we have a factor of 1. So here the energy is twice as big. Here the energy would be one half. Plus the sign difference. So let's discuss what each one would do. Sign, remember we got triple and the singlet state with that. Here you would get singlet up, triplet down. That's one effect. Second, we discussed the radiation having a wavelength lambda equals 21 centimeters. See, epsilon is equal to hf, is energy of the photon, hc over lambda. So lambda goes as 1 over e. If you reduce e, you are increasing epsilon. So if the energy is reduced by 2, lambda would go from 21 centimeters to 42 centimeters. Namely, when we look at the skies, we should see as the hyperfine structure, not 21 centimeter wavelength, we should observe 42 centimeter wavelength. And we should in the lab observe singlet up, triplet down. Whereas it's the other way around. Triplet is up, singlet is down, and we are not observing 42, we are observing 21. So this is telling us something. What is it telling us? It is telling us that the magnetic dipole is not of this form. Even if you don't have magnetic monopoles, you can still have equal numbers of positive magnetic charges and negative magnetic charges. For example, you can form minus Qm plus Qm and D. This is a magnetic dipole, no magnetic charge, total magnetic charge is 0, but there is a magnetic dipole. It is saying that no, the magnetic dipole of the proton is not of this form. It is coming from the electric current circulating inside the proton. So this picture is out. This picture is out means, all right, we are again going back to the our homogeneous equations, and magnetic dipole moment really is proportional to R cross J dV. Namely, it is the circulating electric current that is giving the magnetic dipole, not the arrangement of equal and opposite charges of the magnetic charges. So that we are not observing from the universe 42 centimeter line, but we are observing 21 centimeter line, and that we have triplets up and singlets down in the hyperfine structure is telling us that the magnetic dipole of the proton elementary particle, it's not so elementary. It's just that it is due to the, not due to the arrangement of equal numbers of positive and negative magnetic charges, but it is due to the circulation of electric charges. Therefore, where is it? Out with that. This is out. All right. This is the correct one. what we did before. So, summary of everything so far. We discussed the hyperfine interaction. We took the L equals 0 s orbitals and we computed it with the contact term. And then in the second part we discussed the form of the interaction coming from the classical electromagnetism. And finally we discussed using the symmetry of the Maxwell's equations, extended version of the Maxwell's equations, that the contact term can come in two ways. The one that is due to the equal and opposite magnetic charges is not right, but this is the right one which we have calculated with. Thank you.